Assalamualaikum, very good morning again to all students. So today we meet again for another chapter, for another video about chapter 3, digital system and digital circuit. So I'm Dr. Sharif Fauzi Kamruzama, presenting to you from University of Malaysia Pahang. So for those who already subscribed to my channel, thank you very much. Okay, I appreciate those likes. And for those who haven't, please do subscribe my channel for further more videos later on. Okay, so today we are going to continue our chapter 3. Okay, so in chapter 3, okay, last time we talked about the basic of transistors and how we are using them for digital circuit. So in this video, okay, I would like to introduce to you about what exactly the logic gates and how we are going to use them. Okay, so in logic gates, okay, for example, here we have at least 6 main logic gates that we have inside our computer, okay, which is the AND gate, the OR gate, the NOT gate, the AND gate, and the NOR gate, and also XOR gate, okay, which is the exclusive OR gate. So the AND gate, basically they start with, okay, when the input is either 0, okay, the answer will always be 0. Okay, so if input has a 0 inside it, okay, output will always be 0. Okay, so this is an AND gate, and the symbol of AND gate is look like this. Okay, for OR gate, okay, if an input is always 1, okay, one of the input or any of the input is 1, okay, so the answer will always be 1. Okay, so this is OR gate. Okay, if you have two input, in case here, if either of the input is 1, the answer is 1. If both is 1, also the answer is 1. Okay, so the NOT gate is the gate that always produce an opposite value of the input. Okay, like for example, the input is 0, the output will be 1. If the input is 1, the output will be 0. And then we have an AND gate, NAND gate. So it's usually mentioned as NAND gate. Okay, so for NAND gate, okay, it's opposite of an AND gate. Okay, so it's like an AND gate attached to a NOT gate. So if any of the output has 0 in it, okay, the output will be always 1. So this is a NAND gate. Okay, so NAND gate, basically you draw it like this. Okay, why? Because it's an AND gate and NOT gate combined, and you get the NAND gate. Okay, and then we have a NOR gate. NOR gate also is the opposite of an OR gate. Okay, so means that if in the output, okay, there are 1, okay, the output will always be 0. So it's basically for NOR gate. Okay, so you see that it's an OR gate with a NOT gate attached next to it. Okay, so this is where we got a NOR gate. Okay, so last one is one of the most important one, or we have the XOR gate. Okay, so XOR gate is like an OR gate. Okay, however, when the output, okay, is 1, both of the output is 1, okay, it becomes 0. Okay, in case there are 2 input here, okay, both of the input is 1, it becomes 0. Okay, so if input is both 0, becomes 0, input is both 1, it becomes 0. So in case there are any input that represent, okay, the same one, it become 0. If it's a different one, it become like OR, which is 1 and 1. Okay, so and we have a NOR gate. Okay, so we have XNOR gate, XNOR gate. So here in this case is just the opposite of the XOR gate. So means that if an XOR gate is 0, 1, 1, 0, XNOR gate, okay, XNOR gate, okay, so you get it as 1, 0, 0, 1. Okay, so this is the basic logic gates you need to remember. So the logic gates that you have, okay, so the main one, okay, is AND gate, OR gate, and NOT gate. Okay, you have these 3. Okay, so when you are dealing with calculation, like for example, you want to construct a module for calculating addition, for example, this is where XOR become useful. Okay, so this is the difference between okay, NOR and N, okay, so NOR and NAND gate. Okay, so here in this case there are a NOR gate in terms of this one where the NOT is after the OR gate, and here the NOT is before the OR gate. However, the result will be the same one. Okay, here is not after the AND gate, and here is not before the OR gate. Okay, so it's the same one. Oh, okay, so not after an OR gate is the same as not after an AND gate. Okay, and this one, a not after an AND gate is the same one as a not before an OR gate. Okay, so you see, this one is OR, this one is OR, this one is AND, this one is AND. So this one can represent the same function. Okay, same function. Okay, so this, I mean this one is representing the same function. So if you see that here, okay, x bar plus y bar is equal to xy bar. So it's the same as this one. So this one, both of them representing the same function. Okay, the top one and the bottom one. However, the component that they are using is different. Okay, this one on the left is that they use the NOT gate after the AND or OR gate, and this one, the NOT gate is before the AND or OR gate. So in this case, okay, like for example, okay, so you have an AND and OR gate, they can have more than 2 inputs. Okay, like for example, in this case, okay, so here, okay, so you have, okay, x, y, z, which is from 0 to 7. Okay, you have this input, okay, and you want to create this output, okay, x plus y bar z equal f. Okay, so now, okay, so you have to start with 3 inputs. You have this OR gate. Okay, so OR gate is x plus y plus z. Okay, now you want to have, okay, x, y bar, z. Okay, so x, y bar, z, you just put a NOT gate, okay, after the y. Okay, so this is x, y bar, z. Okay, so in this case, okay, where you have this one and add with an x. Okay, so you have the x plus y bar z. Okay, so this is representing this one. Okay, you see, y bar is here, not, okay, and then you have z, and then you have x. So you combine everything like this one. So you have a not and an or. So you get x plus, okay, y bar z. So this one is y bar z, and you got plus x later on. Okay, so in this case, okay, what kind of circuit do you have? Okay, what is this have? Okay, if you see that here, x and y, so on the top here, okay, so let me open it again. Oops. Okay, so on the top here, so this one is x times y, because it's a AND gate. So down here, so you have x, y bar. No, it's y, z bar. So you can use a symbol, no, you can use equation. Okay, so here you can use accent here, and then you can put any bar here. Okay, so you have z bar. Okay, and then down here you have okay, down here you have x, y, and z, 3. Okay, so at the end, your answer here is XYZ plus with this one and also plus with XY. Because it's an OR gate, so it's plus. Okay. Okay. So F is XY, YZ bar plus XYZ. Okay. So this is how we represent the Boolean algebra. Okay. So and then we have, for example, this is using only NAND gate. Okay. So X. Okay, if you use this one, you got X bar. X times X is X, so you got X bar. Y times Y is Y, you got Y bar. Okay, and here you got X bar times Y bar bar, so you got X plus Y. Okay, this one you can convert it into this one. Okay, so here is, for example, this one also known as NOT gate. Okay, NAND gate. If you use NAND gate for the same input, it become a NOT gate. Okay, and if you use two NAND gate, okay, one you use as usual, and then you add it again with a NOT gate, it become an AND gate, because this one NOT result here is nullified by this NOT result. Okay, so here is example of NAND gate chip. Okay, so you have this kind of chip, okay, available to you in any computer components, this kind of chip. So this one is what we call integrated circuit. So you just connect this pin to another pin, okay, depending for what you want to use. Okay, so when you want to create, like for example the above, this one, okay, these two, okay, this in this case you just connect, okay, this one with, like for example number 4, and then you connect this number 4 again to number 3, and then you got the result at number 2. So in this case, when you got input in 7 and 6, okay, and then you connect the result from 5 to 4, okay, and 4 connected to 3, you will get your answer at 2. Okay, in case you want to conduct same thing like this. Okay, so now for logic circuit design, so basically we have 3 steps. So the first one, you need to draw your truth table first. So you need to draw the table, okay, insert the input and output. From here, you find out what kind of equation that you can create. Okay, so if you can find the equation that you can create, okay, it's a good thing. And then you create the logic diagram based on the Boolean function that you have. Okay, so for simplification, okay, means that you try to remove as much as possible from the truth table to create the Boolean function. Okay, so sometimes we even have the Karnaugh map. So Karnaugh map I'll reserve for later. Okay, so for now, let me explain to you how we can create this table. Okay, so one way we can create this table is by lining up the possible answer to 1. Okay, so in this case, f equal x. Okay, in this case, f equal y. No, with this one next is f equal z. Okay, this one is f equal x. Okay, and then this one if f equal x plus z. And this one equal f equal f y plus z. And last one, f equal x plus y plus z. So now, on the right side here, we combine every equation that result in 1. So how do I get this one? This is because when z is 1, f is equal 1. So f equal z. So here, if f is 1, x equal 1. So in this case, okay, f is 1 equal x plus z. Okay, in this case, f equal 1 is y plus, no, x plus y, sorry. X plus y. Okay, plus y. And here, x plus y plus z. So now I want you to combine everything into one equation. So x plus z plus x plus s plus y. Okay, and then between this you plus again x plus z again, and then plus x, and then plus z. Okay, so you get this equation when you combine all of them. Okay, you get this equation when you combine all of them down here. So from here, okay, how do you simplify so that, okay, I'm sorry, so this is wrong actually. So this one, okay, now I would like to explain to you how we are going to do this. Okay, so let's start with, okay, how we can conduct this. So I need you to find the ones first. Okay, so in this case, okay, f equal x bar, y bar, z. So you can click insert equation here. Okay, equation and accent, and here you can add. So here x bar y bar okay, and z. Okay, so here is the first one, and then you have the second one is x bar, y bar, z bar. So this one's supposed to be z. So z. X, Y, Z. And then the third one is x bar, x, y bar, z bar. The third one is x, y bar, z. So this one is just z. Z. And then you have, here is x, y bar, z bar. And last is x, y, z. Okay, so we finish the first step. Okay, you find all of them with ones, and then you finish the first step. Now, I want you to combine everything into one equation. So here, when you want to combine, you can combine this one with, okay, the result of this, and then the result of this, three, okay. So you got this equation combined here. And then next we need to simplify this equation based on certain rule that you can get. So one way to simplify, okay, if you can find out something match, like for example here, xy and xyz and xyz bar, you can simplify it into f equal xy z plus z bar. Okay, so you got 1 to eliminate 1 here. So this one you can eliminate. Okay, in this one you can eliminate this one. Okay, we finish with the first one, and then we try to add with the next one. What you can get here is also the same xy bar, z bar, and xy bar, z. So here you can get this one again, and here you can, so this one here. So we finish with this one here and here. Okay, and then the third one, so you have, okay, here you have x, y bar, z. So when you have, okay, this result, next, what you need to do is, you can scratch this into 1, change into 1, because based on the rule, one of the logic gates rule, okay, and a variable plus a variable bar, it can become 1. Okay, so this one is equal 1. Okay, and then you'll get f. Okay, you can simplify next, okay, by getting this. So because of this is 1, you can remove, and this one you can remove. Okay, next you can get x, okay, with x bar plus y. Okay, you can get something like this. So here, at the end, you can get f equal x bar okay, you can get x, okay, x plus x bar y bar z. Okay, so here one trick you can do, okay, is that one trick you can do is that you want them to times 1. Okay, in this case, and this also times 1. Okay, I think this is the lowest I can get here. I think the answer here I provided is wrong. Okay, supposedly the answer is this one. Okay, but you can get, sometimes you can get almost similar answer with other kind of equation as well. Okay, so it depends on how you calculate them. Okay, at the end when you create the equation, you can get something that looks like this. Okay, so this one I think a little bit wrong. Okay, so how it should be corrected is that here is you have another bar here. Okay, and then you have okay, another bar here that attach to here. Okay, and then you have this one. Okay, and then this one, and X is going directly here. Okay, and then we have another one, okay, of the here, over here, start from here, going directly to the OR gate. Okay, so supposedly your gate should look like this. Okay, I think this is the PowerPoint here is I'm using is quite old. It doesn't manage the new one. So here is example of the how you construct the logic circuit design based on the Boolean algebra. So you can see here you have an AND gate that combines X bar, Y bar, and Z, and you have an OR gate that combines X, Y, bar, and Z with X plus X. So this is the result that you can get at the end of the exercise. So I think that's all for today. So I'll continue everything. Okay, where I'm look forward for your question and answer, your responses. Okay, during our lab session later on. So I'll see you guys later on in my next video as well. So hopefully, okay, you stay tuned to the things that I'm going to teach you later on. Okay, so that's all from Dr. Shafiq. Bye bye.